So, today we will begin with our lecture 16, which is regarding minimum energy point and discussion on applications of circuit and system design on minimum energy point, and this is a part of module 2. So, we will discuss the minimum energy point model, which we had discussed in the previous lecture. So, we will continue from there, and also we will discuss what is the optimum threshold voltage, and we will discuss the constant energy and delay contours and how we find out minimum energy for a given speed, and we will discuss the implications of system level decisions on minimum energy point. So, we had discussed the minimum energy point model, which was 2 minus VDD by NVT, where VT is the thermal voltage, into exponential 2 minus VDD by NVT is equal to minus 2 alpha C effective by I naught W effective CG LDP. So, this is a model which we had derived in the previous lecture. So, now what is alpha? Alpha is, for a reference, let us write down alpha is switching activity factor, LDP is the logic depth in terms of inverter delays, CG is inverter's input capacitance, and C effective is effective switching capacitance of the circuit, and W effective is the effective width for leakage of the entire circuit, and I naught is a constant. Okay. So, what do we see here? We see that the right hand side is negative. What does it mean? It means that VDD should be greater than NVT of the order of say 50 millivolts at room temperature. So, now what do we say? So, for very small VDDs, our models are not valid, and what are the other implications? If alpha or C effective increases, if alpha C effective increases, what happens? The negative right hand side increases, negative value in magnitude. When can that happen? When VDD by NVT is, though VDD by NVT is larger than 2, because we have an exponential term here, this should be, since this is large in magnitude, this should be also large in magnitude. What do we mean to say is that this VDD minus VDD by NVT should become smaller in value, because this is larger than 2 and it is a negative exponent. So, the negative exponent's value should become smaller. So, VDD by NVT should be smaller. If you increase alpha C effective, this should become smaller. So, that corresponds to our earlier discussion. Well, so what did we say earlier? So, when you increase the switching capacitance in a circuit, then dynamic energy increases and leakage energy stays the same if you are not changing the VDD, or so the time period almost remains the same. So, you find that the leakage energy remains the same, but now you are increasing the value of alpha C effective. So, dynamic energy increases. If you reduce the value of VDD, the time period increases and therefore, leakage energy increases, but dynamic energy reduces. So, you reduce the value of VDD and increase the leakage energy and reduce dynamic energy. So, you find a new optimum. So, therefore, this actually increases the value of VDD optimum. What about W effective? When W effective increases, what happens? You find that the exponent, so the negative value here increases in magnitude. It means this should be negative, but the value of VDD by NVT should increase. So, that the negative exponent increases, this reduces in magnitude, this also reduces in magnitude. So, let us see how this corresponds to our earlier discussion. So, when we increase the leakage currents, that is, you are increasing W effective for leakage. So, you are increasing the leakage currents. So, if you increase the value of VDD, the dynamic energy increases, but the time period reduces. If VDD optimum, it increases because time period reduces and E dynamic reduces, E leakage, E dynamic increases, E leakage reduces. So, when you increase the value of W effective, because leakage currents have increased, so leakage energy increases. Now, you want to reduce it. So, you increase VDD, time period reduces, leakage energy reduces, but dynamic energy increases. So, you find a new optimum. So, what happens with increase in LDP, that is logic depth? So, you in the same circuit within a time period, now you are having larger number of stages. Switching will happen only at one of the stages. So, therefore, at a time. So, therefore, it is leakage energy which you are increasing per cycle within a data path. So, if you look at the energy within a data path, you will find that the leakage energy increases. So, now to reduce leakage energy, you would have to increase the VDD and thereby reduce time period, you reduce the leakage energy, but you increase the dynamic energy. So, you get a new optimum VDD which is larger than the earlier optimum VDD, it increases. So, because switching happens at one of the stages in a data path and number of stages which are idle increases. Okay. So, the leakage increases. Now, let us define this right hand side by beta. So, we are saying beta is 2 alpha C effective exponent of 2 divided by I naught W effective CG LDP. Now, this is a kind of a value which actually determines the optimum VDD. So, if we plot this beta with respect to optimum VDD, what do we find? So, as you increase beta, that can be because you are increasing alpha or you are increasing C effective or you are reducing LDP, whatever be the reason. If you increase beta, VDD optimum reduces. So, the beta by increase I mean increase in magnitude. So, since beta has a negative value, the right hand side has a negative value in the expression for minimum energy point. So, now that is a, so you will find an increase means it is reducing in the magnitude. Suppose the value of beta is minus 0.1 here, it is minus 0.01 like that, 001. So, you will find that as the magnitude of beta is reducing, VDD optimum keeps on increasing. So, and it would increase. So, how much does it increase? Now, that depends on the circuit, because so how are you calculating LDP? For example, in a ring oscillator, the logic depth, how should it be taken? It should be 2n, because there are 2n stages. So, that could be a simple example. So, what are we essentially doing? So, if we plot the energy versus VDD, what happens to the dynamic energy? As we know, the dynamic energy keeps growing. And what happens to the leakage energy? If we plot on a log scale, so, if we plot on a log scale, you will find that the leakage energy would almost remain constant here. So, what are we essentially doing to find out VDD optimum? We are looking at the tangents, tangent of the dynamic energy and the tangent of the leakage energy. So, wherever the tangents have equivalent so now the tangents have equivalent opposite, I mean they have opposite signs. So, tangents of E dynamic and E leak have opposite signs. So, wherever the tangents have equal values, equal magnitudes, that is the optimum VDD. So, wherever the change in reduction in dynamic energy and increase in leakage energy with a reduction in VDD is equal, you have the optimum VDD. So, this is what essentially we were doing. Now, how would we find out C effective and W effective, extraction of C effective? So, for a given circuit or system, we would run the circuit over a long period and with a given frequency. In that case, on an average, all the capacitances which switch would get charged and discharged in one cycle time. So, you have a capture flip flop, launch flip flop and a capture flip flop and a data path in a pipeline stage or a logic path in a stage, pipeline stage. So, now within one clock period, every stage of the logic path would switch. One clock period T, each stage of a logic path between a capture and launch flip flop would switch. So, in that case you would, so you have a scenario of this kind. You have a flip flop, some random logic 1, another flip flop, random logic 2, like this. So, within a clock period, one of the stages would switch in this, and in the same clock period, one of the stages would switch in the next pipeline stage also. So, within a clock period, you would find that all the capacitances involved charge and they would get discharged in the subsequent clock periods. So, over a long period of time, the rate at which the capacitances would get charged and discharged, if you, so it would be across the, for a given number of cycles, they would get charged and discharged. So, it would get either charged or discharged in a few cycles depending on the kinds of inputs that are coming. For over a long period of time, you would say that on an average they get charged and discharged in a few cycles. So, it is a frequency dependent charging and discharging of the capacitances. Therefore, you can say that if you measure average current flowing through, suppose there is this power supply. So, average current that is supplied to these logic paths, it would be equal to the capacitances. So, total capacitance into VDD. So, it is charged to VDD and again discharged. So, at what frequency? At frequency f, frequency of operation f. So, this is the average current. So, the effective capacitance is measured as average capacitance divided by VDD into frequency. So, over a long period for several cycles, you average out all the kinds of inputs that are coming. So, in that you get the effect of all the inputs that are coming. So, you have an average value of and you measure average current over the entire large number of cycles. So, you would charge and discharge all the capacitances with a frequency which is proportional to the clock frequency, and therefore, you would write the effective capacitance as average current divided by VDD into frequency. So, you are assuming that all the capacitances they are getting charged to VDD and discharged. So, taken together it is like an effective capacitance. What about effective width extraction? To extract effective width of a system, clock is stopped, so that there is no switching which is taking place and the entire system is in a steady state. So, that would give us a leakage current, total leakage current. However, it would give the total leakage current for a certain state. So, now leakage current, as we had discussed, we had seen the example of NAND gate in one of the previous lectures. So, we saw that the leakage current depends on the input values. What are the input values? So, it would therefore, the leakage current would actually depend on the input state of the system. So, what is the value of, say, in this example, what is the value of Q1, what is the value of Q2, what is the value of Q3. Depending on that, when you stop the clock, you would have different leakage. So, and where do you measure I leak? You again measure it here from the power supply. So, I leak is a function of Q1, Q2 like that. So, now it is a function of state. So, you should simulate over a large number of states and find out when the clock is at a certain state what is the current. Average out all the currents. So, average out all the values of the leakage current for different states Q1, Q2 etc. So, that average current is I leakage. Now, find out I leakage of inverter averaged for the input V being 0 and VDD, okay, for the inverter. And so, to get the W effective in terms of inverter width, just take the ratio of I leakage of the system with that of I leakage of the inverter. Now, this could be an inverter of a certain size that you take as reference, and it is not preferable to keep the minimum sized inverter because their narrow width effects may start dominating. For reference. But this should not be minimum sized. Otherwise, narrow width effects dominate, inverse narrow width effect or narrow width. How do we find out LDP? So, now for LDP, we run timing simulations and find out critical paths for different inputs. Take the average timing simulations for different inputs, average the critical path delays for all these timing simulations with different inputs. Now, the critical path delay average divided by delay of the reference inverter is the logic depth of the system. So, now using these three we can find out if we, and when we know the activity factor, we can find out the optimum value of VDD or minimum energy point. What is the implication of a change in threshold voltage? So, when you increase threshold voltage, you would reduce the leakage current, but you would increase time period would increase. So, therefore, leakage energy should increase. What happens to the dynamic energy? That should not change. Leakage current reduces and the time period increases, delays increase, leakage current reduces. So, leakage current would reduce exponentially, time period would also increase exponentially as we had seen in the previous lectures. So, leakage energy may not change. So, with threshold voltage increase, you do not find a great impact on the VDD optimum, and that is what our model also says. In the model, there is no term related to threshold voltage. So, if we have a handle on threshold voltage, suppose the body bias of a FDSOI device, that is a handle on threshold voltage, or maybe due to process optimization, if you have a handle on the threshold voltage, then do you not have an optimum value of threshold voltage? Our minimum energy point model does not have threshold voltage as one of the parameters. The reason we have just discussed. So, the total time period in the previous lectures we had taken it to be the delay of an inverter into logic depth. So, this is Cg, the gate capacitance, input capacitance of an inverter or FF4 load. So, it is proportional to the capacitance of the inverter. VDD, now we are dealing with optimum value of VDD. So, VDD optimum divided by I naught exponential. So, now this is the current VDD optimum minus threshold voltage, and this is 1 by frequency. So, what is the value of VTH for this VDD optimum? So, it is VDD optimum minus NVT VDD optimum LDP F divided by I naught. So, what does this give us? So, for a given, so now for if you have a VDD, you have come up with a VDD optimum. Now, to obtain a certain certain speed of the system, that is certain clock frequency of the system, what is the threshold voltage that you should have? So, you may not get the desired frequency that you want with the given threshold voltage for your VDD optimum. Now, you want to have a desired frequency of operation. What you would do is that you would adjust the body bias, etc., in such a manner that you get this value of threshold voltage. That is the idea here. Now, let us look at the implication of the switching activity factor. So, how one would extract the switching activity factor? So, this circuit would give us for a given PDK and a given standard cell library, this could give us good estimate of the relation of minimum energy point with switching activity factor. So, now this is a ring oscillator, say 11 stages, and you have delay lines, 11 delay lines again of each of 11 stages. So, 11 is just an example here. So, now you drive this node of the delay line with this node of this ring oscillator and this of the second delay line with this node of the first delay line, like that. Likewise, you have. So, now all these delay lines have equal number of switching and equal power, equal delays, etc. They are all symmetric in that sense. If S1, S2, S11 are all VDD, are all 1. In case, suppose you want to emulate for an activity factor 0.5, what would you do? From S1 to S5, you can have 1 as the input, and from S6 to S11, you can have 0 as the input. So, now you have 6 of these parallel lines, 1 ring oscillator and 5 delay lines switching, and the other 6 are not switching. So, you have an activity, you emulate an activity factor of 0.5. All of them are having the having leakage current consumption, but switching is happening only on half of them. So, that is how you can emulate for different values of switching activity factor, and you have a minimum energy point, but you in this way you also get contours of for different alpha, you get the minimum energy point, and also changing the VDD you can find out what are the contours of equal energy. Why is this useful? We will discuss. So, with you can find on this and this parts of the contour of equal energy. So, minimum energy is somewhere here. So, this is equal energy 2x the 2 times the minimum energy. So, here you find that with increase in threshold voltage, leakage current reduces, time period increases, I leak almost remains constant. So, I total remains constant. That is how you can explain this. Here with an increase in VDD, you would find that dynamic energy increases, and so the time period reduces, and threshold voltage therefore can be reduced. So, the threshold voltage also can be reduced. So, this part how do you explain? You increase the VDD, so time period and also VTH. So, dynamic energy increases, time period reduces. So, therefore, leakage energy overall it reduces. So, therefore, the total energy remains constant. What about this part? So, here you are increasing the threshold voltage. So, leakage currents reduce, time period increases, and therefore, leakage energy almost remains constant and total energy remains constant. So, likewise you can explain different parts of this contour, and why is this useful? So, now on this contour if you also draw equal delay or constant delay contours, so they would come out like this, because you are changing threshold voltage and also you are increasing threshold voltage and also increasing VDD. So, almost the overdrive you are keeping it constant, and therefore, it is a constant delay in the sense that you are not changing VDD minus VTH. So, the currents remain the same and therefore, the delay does not change much. So, you may not find a straight line, but it is a curve which is, it is a non-linear curve, but for small changes in VDD and VTH it would look like a straight line. So, now wherever suppose this curve intersects the 1.5x contour at this point. So, for this speed you can get a minimum energy consumption of 1.5x. So, for example, here you get energy consumption of 2 times the minimum energy possible. So, that is so wherever the constant delay contour touches the constant energy contour as a tangent, that is the minimum energy possible for that value of delay. Constant delay contour tangent of constant energy contour. So, this is the minimum energy for the desired delay. So, that is what is given by this point. So, the same results you can see for a 45 nanometer PDK and also for a 180 nanometer PDK. So, 180 nanometer PDK results are from the papers of Ananta Chandrakasan's group, and this is from students in our institute. So, now you can see that these constant delay contours, these touch the constant energy contours here. So, this touches this almost like a tangent. So, you can have a minimum energy of this for this frequency. Now, what happens when you increase alpha? As we had seen earlier, when you increase alpha, the minimum energy point rises. So, that is what is happening. Here it is here and here it has risen. What happens when you increase temperature? So, if you increase temperature, the threshold voltage would reduce, and therefore, you would find that. So, now what is the implication of change in threshold voltage on minimum energy point? So, as we had seen, the minimum energy point does not change much with a change in threshold voltage. So, that is why optimum is a weak function of threshold voltage, and therefore, temperature has a small influence on the minimum energy point. What about pipelining? If you increase the pipeline stages, then logic depth reduces, and you can find out that because logic depth reduces, therefore, the optimum VDD, since leakage energy reduces, you can increase the reduce the time period, that is increase the optimum the VDD, and you can increase the dynamic energy increases and the optimum VDD increases. So, what happens for increase in parallelization? If it is increased, so number of parallel paths now increase. So, that would also increase the switching activity. So, if it increases switching activity, then you would find that the optimum VDD reduces. So, there are system level, so the system level implications also have an impact on the optimum VDD or minimum energy point. So, today we have discussed optimum VDD, how we can obtain it for a system, and then we also discussed an experiment to find out for different switching activity factors for a PDK to find out the optimum VDD, and we discussed optimum threshold voltage for an optimum VDD, and we also discussed the system level implications, decisions of system level at the system level, what implications these have on optimum BDD. Thank you.